Okay, some more of the 2003 BC multiple choice test. And here we have number 25. The function f is continuous on the closed interval 2 to 14. And as values shown in the table, using subintervals 2 to 5, 5 to 10, 10 to 14. What is the approximation of the integral from 2 to 14 of f of x found by using a right Riemann sum? So I kind of put a little sketch here. These are my intervals, so you just can see. And this is going to be the 12, the 28, the 34, and the 30. So if we're going to use a right Riemann sum, we're going to use the right endpoints. 1, 2, 3, or these right endpoints here. 1, 2, 3. If it was a left Riemann sum, we'd use these 3. But it's right, so we're going to use those for my bases and my for the altitudes or the heights of my rectangles, and the bases are given by from 5 minus 2 is 3, 10 minus 5 is 10, 4 minus 10 is 4. I'm sorry. 5 minus 2 is 3, 10 minus 5 is 5, 10 minus 5 is 5, 14 minus 10 is 4. So these were my bases 3, 5, and 4. And these were the heights, so these were my 3 areas. Base times height equals the area. It's just which side we use for the altitudes here. So we've got 3 times 28, 5 times 34, 4 times 30. So 3 times 20 is 84, 5 times 4 is 20. I carry your 2, 15, 17, and 120. Then I added them before here. I got 374. Okay, then we want to integrate this number 26, and this was just an integration by partial fractions. I'm sorry, partial fractions. So we rewrite this 2x over this denominator equals, we're going to break this up, a over x plus 2 plus b over x plus 1. Then we work over here, so we got a times x plus 1 plus b times x plus 2. If we put these all over a common denominator, equals 2x. So these would be the numerators over this denominator. So if the denominators are equal, the numerators are equal. And then we just go ahead and we try to find some values that are going to get one of the variables to disappear. So when x is negative 1, negative 1 plus 1 is 0. So my a goes out. So I've got b equals negative 1 plus 2 is 1. And if I put negative 1 in here, 2 times negative 1 is negative 2. So b equals negative 2. And then if I put negative 1 and negative 2 in here, the b zeroes out, and I've got negative 2 plus 1 is negative a, and if I put negative 2 in here, 2 times negative 2 is negative 4. If negative a equals negative 4, a equals 4. So I can rewrite this now. I can write this integral as the integral of 4 over x plus 2, and I broke it up, plus the integral of negative 2 all over x plus 1. So I kind of broke this up into 2 integrals, like this. And this is just the natural log, so this is the natural log of, this is 1 over u du, so this is just the natural log of the absolute value of x plus 2, with a 4 in front, because we had a 4 here, so we could put that in front. We could put the negative 2 in front here, and then we have the natural log of the absolute value of x plus 1, and then plus c. Okay, so this was just a nice integration by partial fractions. Okay, not too hard, just have to be careful. Okay. And number 27, good old fundamental theorem of calculus. The derivative of the integral is equal to just the value of the function. This is the dummy variable. And this is what we've got over here. So the derivative of the integral, so every time I see a t, I'm going to put an x cubed. So it's going to be the natural log of x cubed, x squared cubed, which is x to the 6th, plus 1. But then I need the derivative of this, which is going to be 3x squared. So you can then that's it. And that's what they just put the 3x squared in front, natural log of x to the 6th plus 1. So that was a nice, easy one. Just have to know the fundamental theorem of calculus. And then number 28, the Taylor series. What's the coefficient of x squared in the Taylor series? Well, we know the Taylor series, if we look at the expansion, it's going to be, and this is about x equals 0, so it would be, We know the first term is going to be well, I'm sorry. It's going to be f of 0 f prime of 0 okay, and this is going to be x squared, so when we simplify this out, it's just going to be, we look at this one over here, this is going to be f double prime of 0 all over 2 times x squared, so this is what we're looking for right here, this coefficient of the x squared. Alright, and you do this, this is why I asked you to write it out every time, so it just becomes automatic when you have to write that Taylor expansion out. So we're looking for the second derivative. Alright, well this is the Taylor series, this is my function, so that's my f of, there's my first order, f. So I need to take the second derivative and the third derivative and evaluate those at 0. Well, I just only have to evaluate this one. So this is my f, so what's f prime of x? This is f of x. F prime of x would equal, and f second of x would equal. So this is f of x, so I can put this up on top. It's a little bit easier to take the derivative using the power rule, so negative 2 times 1 plus x to the negative 3. There's no chain rule because this is 1, no problem there. And then that's going to be 6, 1 plus x to the negative 4. So that's my second derivative. And I wrote them over here in fractions. And we want to evaluate the second derivative because we're really looking for the second derivative over 2. So the second derivative is going to be this at 0. So that's going to be 6 over 1 plus 0 to the 4th, which is just 6 over 1 to the 4th, which is just 6. All right? So that's going to be 6 over 2. So 6 over 2 times x squared. So that's what we're looking for. And that just ends up being 3x squared. And they're looking for the coefficient of the x squared. So that's just going to be letter D, 3. Okay? So that's a nice application of your knowledge of the Taylor expansions and the derivatives. And that was 28. Okay? Hope that helps.